Hello, I'm pleased to congratulate you with the second revolution in uniting math and computer architecture. The first one was when people started to implement math functions such like sinus, cosinus, tangents, exponent in computer hardware. Now we implement in computer hardware a partial differential equation. So we can speed up computations in many useful application domains and make some infeasible problems feasible. We are interested primarily in embedded system design. For embedded system design, we consider such target devices as microcontrollers or field-programmable gate arrays, FPGA. We are using design approaches on bare hardware or within the environment of real-time operating system. We apply direct coding in some programming language, model-driven development, which is rather heavy for embedded system design, and our preference is formal method-driven development, which we offer to follow because with formal or mathematical method-driven development, we can prove correctness of systems in a strict mathematical way to provide reliable embedded system design. And now let us consider workflow for our technique. So at first we have boundary problem for partial differential equation. Many useful tasks are specified in this way. For instance, thermodynamics, gas or liquid dynamics, diffusion, and other processes. Optimal control for some domains. We apply finite difference methods, so we choose a stencil and we study convergence issues. After we are sure that there is convergence, we implement this finite difference scheme on Sleptsov Net Mesh. We are using Sleptsov Mesh as an intermediate construct to study finite value approximation, non-negative integer approximation, and prove some properties, for instance, liveness, and study some maybe timed properties as well. Based on Sleptsov Net specification, we generate Verilog code, and then using instrumental software for target FPGA, we compile, route and place, and upload this Verilog code onto the target device. It is running in non-stop way, this mesh of finite difference method. We attach sensors to the boundary of this mesh, and from dedicated nodes we obtain optimal control and output it to the actuators. So here in red color we have the output maybe configuration functioning, and in blue color blockchain to prepare and obtain the target code. So here we start with Laplace equation with this case study. When we choose this magical stencil with 8 neighbors of Moore neighborhood, because it reveals very good accuracy of fourth degree. Replacing second derivatives in the Laplace equation following the expression according to stencil, we obtain the finite difference expression, and we recalculate values following this expression in each node of mesh. As for the terminal condition, we consider difference, absolute value of difference between the previous and next iteration and compare with the required accuracy. We illustrate this technique using constant boundary numerical example. And here we are using three-dimensional picture because we have two-dimensional domain and we need the third dimension to represent values of obtained function. Here I would like to provide a second very significant comment. If you have a look on this finite difference expression at the bottom of this slide, you can consider this mesh as a kind of neural network. But in neural network we have movement, one side spreading of values. Here we have 8 side spreading of values according to Moore neighborhood. And here we have this neural network trained by partial differential equation, but we can apply different techniques as well. I would like to mention an intrinsic connection with cellular automata technique, where we compute values of nodes based on their neighbors, and we apply this technique to study integer value approximation of this finite difference expression for solving a partial differential equation. After we obtain this expression, we apply Sleptsov nets to specify the process of integer approximation and recalculation in the nodes of some mesh. You can find references for Sleptsov nets and Sleptsov Net Computing, including some information about this approach on ICM Tech News. A Sleptsov net is a bipartite directed graph with vertices of two types, places and transitions, connected using arcs, maybe multiple arcs. Tokens are situated inside of places and they represent so-called marking. Marking changes as the result of transition firing. So it is proven to be a Turing complete system and it runs exponentially faster than a Petri net which it generalizes. So we are using this formal system to specify integer approximation. And here we illustrate the transition firing rule. For instance, to compute some arithmetic expression. In the first case, we fire transition T1 in 3 copies and transition T2 in 2 copies. So here we find fire transition T3 in 3 copies, 12 divided by 4. We compute firing multiplicity of an arc as marking divided by the arc multiplicity, firing multiplicity of a transition as minimal between firing multiplicities of incoming arcs, and then final expression gives us next marking. Since we are using synchronous Sleptsov net, or so-called Sleptsov-Salvitsky net, because of it, we recalculate all the markings simultaneously, how it is implemented finally within FPGA. We translate this expression into the corresponding pattern of Sleptsov net for one iteration. We regroup terms of the finite difference expression in different way, and because of it, we obtain simple pattern to compute values in one time cycle with lower accuracy, or more sophisticated pattern to recompute the value in 3 time cycle. Based on this constructs, we compose 5 by 5 lattice or mesh. And here we have 3 by 3 inside lattice, which recalculates values, taking some neighboring values from the boundary. So we can specify this kind of spatial Sleptsov nets using these graphical pictures, but in the general case, we need some mathematical expression and we apply infinite parametric Sleptsov net specification. We develop the theory as well. for verification of networking protocols, protocols for grids and clouds. So here we have a parameter n, and because we consider a set of nets according to the infinity with cardinal number measure, so we consider and specify patterns, and we investigate patterns with no regard to their size. Let us consider, for instance, first line, D5 IJ is the name of transition, then input places follow multiplicity of arc and the name of place separated by comma, and then output places. Using this notation, we can compile it into infinite systems of linear algebraic equations to study properties, and two other structures for formal verification and investigation of the performance issues. Finally, we compile this mesh specification into Verilog code. So here into this Verilog code, I would like to attract your attention to this round H parameter. Because we are using finite difference approximation, we need to, when we receive some maybe reminder, we need either to add 0 or add 1 depending on the value of this reminder. And it is a parameter, sometimes it is a good parameter to adjust convergence, because for cellular automata it can be either coming to certain value, because we have 1 at the smallest value after we apply scaling to obtain int value approximation, or we can obtain some pulsing configuration, some loop with low change of values, and it also satisfies maybe criteria for convergence. This Verilog code is inputted to the corresponding integrated developer environment of FPGA producer. For this research, we were using CP Tang Nano FPGAs, which contain Gowin chip, and we were using Gowin FPGA Designer, which is free for academic, for special academic version. These intermediate pictures are just for illustrative purposes, because we are interested in obtaining code for FPGA when this software is synthesizing circuit, when it provides routing and mapping on the corresponding elements on LUTs. Here to the left we can see one node configuration and then mesh configuration, because it is an automatical layout. 3x3 lattice is not regular here, it is just for illustration. By the way, this CP Tang Nano FPGA with 9 kilo of LUTs costs some 10 pounds, and it has a frequency of 27 megahertz, which is rather good for initial maybe training. We are using this kind of PGA for teaching Rolls-Royce apprentices who are very satisfied with this rather simple and powerful instrument. Finally, we obtained a series of benchmarks. First, benchmarks for real number solutions in a traditional way, and compared them to integer approximation on FPGA. For this small Tang Nano 9K FPGA, we can squeeze in mesh up to 9 by 9, which gives us accuracy 1000 in the source numbers, because we have integer. After backscaling, we obtain this accuracy. For bigger FPGA, we were using professional Tang Nano FPGA with 128 LUTs and higher frequency. We obtain better accuracy. Please mind that for 50 megahertz clock, we run one iteration in 20 nanoseconds. With modern FPGA, which provide 1 gigahertz frequency, we can achieve 1 nanosecond scale, which satisfies requirement for control of fast processes, nuclear reactions, turbine control, maybe hypersonic flying objects. Very interesting application domains. And now I'd like to attract your attention maybe to the obtained results. We developed methods, we developed technique for fast math parallel numerical solving of optimal control problems specified by PDE and systems of PDE, of partial differential equations. We applied formal method driven development so we can prove properties of our final specification. For differential equations, we applied finite difference methods and iterational process of their solutions. We specified the integer number approximation using graphical language of infinite synchronous Sleptsov nets or Sleptsov-Salvitsky nets. And finally, we obtained embedded control of fast processes in real time on FPGA. We are on our way to find applications. So we are having PDE running on our small FPGA, bigger FPGA, so we need to attach them to turbines, reactors, etc. And because of it, we invite you to participate in project proposals, and we invite industrial partners to cooperation. And we'd like to show what our advances are rather fast in this direction. So we are working in this direction, publishing, for instance, detailed information about the presented process of solving PDE implemented in computer architecture is in this recently published paper. Additional co-author Tatiana Shmelyova presents HPC aspect to use high-performance computers. She studies interconnects, especially multidimensional torus interconnects like TOFU-D interconnect of Fugaku supercomputer, who, after Jack Dangara Turing Award talk, is considered the most efficient supercomputer in the world. And by the way, the second paper about this supercomputer aspect implementation of Sleptsov nets is co-authored by a remarkable person, a great engineer, Yushiro Ajima, the designer of TOFU-D interconnect, and co-authored by Rolls-Royce representatives as well. The third paper uh, illustrates how we can apply Sleptsov net-based design for embedded system. And here we are not starting from PDE, we just start from any Sleptsov net. We have recent illustration for automated manufacture, for robotic arm connected to storage and rotary table. And the fourth paper is a theoretical paper, and it is example how we should publish our results in our opinion, because it is a very significant proof which is represented on 3 pages with 3 references. And my co-author Bernard Bartholomew is a great French scientist, developer of TINA modeling system, recently extended with Sleptsov net approach, which we are using as IDE for our toolchain. So Here in theoretical computer science, maybe you can find more references to the previous papers published or using this reference for Sleptsov Net Computing. Thank you for your attention. Your questions, offers of cooperation are welcome. On the first slide, you can follow links to my website or to website of my co-authors to proceed with our cooperation. Thank you for your attention and best wishes in uniting math and computer hardware. Thank you.